Hello everybody. I welcome you all back to Unit 14 Biomolecules, Part 3. We should start with the monosaccharide fructose. If you can remember, in the previous video, we had learnt the open chain structure and the cyclic structure of monosaccharide glucose. Fructose, where does it occur? Fructose, the term itself tells us it is having the main occurrence to be found in fruits. It is a ketohexose and because it occurs in fruits, it is also called as fruit sugar. Fructose, when we look at its structure, it is observed that there are 6 carbon atoms where the second carbon atom in fructose is found to be a ketohexose. Why do you call it as a ketohexose? The reason, the second carbon atom here is found to be a ketone, and hence we have in the open chain structure the first carbon atom, which is a primary alcohol, the second the ketonic group, the third, the fourth, the fifth and the sixth carbon atom, very similar to the structure of glucose. Now fructose do belong to the D series, where the OH group on carbon 5 is on the right side. The compound has the ability to rotate the plane polarized light in the anti-clockwise direction. Hence, it is levorotatory, which is indicated with a negative sign within parenthesis. Therefore, fructose is also called by another name, levulose. Fructose is found to exist in 2 cyclic forms. The ring structure of fructose is based on the heterocyclic ring furan. Furan has 5 members in the ring. Out of those 5 members, it is noticed that there are 4 carbon atoms, which I am pointing it at now, and 1 oxygen atom. Therefore, whenever we discuss the ring structure of fructose, it is observed that the OH group on the 5th carbon atom is involved in the ring formation with carbon number 2, the ketonic group. Thereby, in the cyclic structure, the Fischer structure of our fructose in the cyclic form, you are having the first carbon atom CH2OH, the second carbon atom converting from C double bond O to COH, the third carbon atom OH on the left, H on the right, the fourth carbon atom H on the left, OH on the right, the fifth carbon atom H on the left and involved in the ring formation with carbon number 2 through oxygen atom. This is called as glycosidic linkage or hemiacetal form, and the sixth carbon atom CH2OH as it is. Now, as we have on the anomeric carbon, which is carbon number 2, OH on the right side, the compound is called as the alpha configuration. Now, what is the anomeric carbon? Let us recollect. It is the carbon atom which was the functional group in the open chain structure, and it was the functional group and involved in the ring formation now. So therefore, if the OH is on the right side, the structure is called as alpha. The compound belongs to the D series. It rotates the plane polarized light in the anti-clockwise direction, so minus, and it is called fructofuranose. The reason, it's a 5-membered ring as the analogy taken. The furan ring as the analogy taken. So it's called fructofuranose. The other form is the beta. In the beta, only at carbon number 2, the OH comes on the left and the CH2OH group goes on the right. The rest of the carbon atoms will have the same configuration as when compared to the alpha. Therefore, the beta D-fructofuranose, what we have, is an enema of the alpha D-fructofuranose. So these two are the Fischer structures of fructose. Now, when we refer to the cyclic structures of the two anomers of fructose in the Haworth form or the configuration, in the Haworth configuration, you take the furanose ring as the analogy. This is the ring of a furan. We have oxygen and from there we have written or drawn the furan 5-membered ring structure. We are labeling the carbon atoms as carbon number 1, this is 2, this is 3, 4, 5 and 6. If you compare it with the open chain structure of our rather ring structure of fructose in the Fischer form, the rule says whatever groups are present on the left side of the carbon skeleton should be going above the plane and whatever is on the right side should be written below the plane. So let us check carbon number 2, 3, 4, 5. They are all the members of the ring. Carbon number 2 has CH2OH on the left and OH on the right. So therefore CH2OH above the plane, OH below the plane. Carbon number 3, if you will compare, OH on the left, H on the right. So carbon number 3, OH above the plane and H below the plane. Carbon number 4, H on the left, OH on the right. So carbon number 4, H above the plane, OH below the plane. Carbon number 5, H on the left and is involved in the hemiacetal ring formation. So carbon number 5, you are having the hemiacetal ring formation here. The bulky CH2OH is put above the plane and hydrogen below. The structure is now called alpha D minus fructofuranose. The Haworth structure is the one which you need to remember and practice and write in the examination. This is the one which is generally asked in the examination. Now let us look at the beta structure. When you are writing the beta structure, the configuration only varies at carbon number 2. In the beta D-fructofuranose structure, at carbon number 2, the OH goes above the plane and CH2OH comes below the plane when you compare it with the alpha. If you look at the alpha form, at carbon number 2, CH2OH is above the plane, OH is below the plane. When you come towards the beta configuration, at carbon number 2, OH is above the plane, CH2OH is below the plane. Carbon number 3, 4, 5 and 6 have got the same arrangement of the OH and H groups as compared to alpha D fructofuranose. So, as they differ only in the configuration around carbon number 2, which is the anomeric carbon, alpha D minus fructofuranose, beta D minus fructofuranose are called as anomers. Let us now proceed towards the disaccharides. Amongst the disaccharides, the first disaccharide we come across is sucrose. It is of D plus glucose and D minus fructose. You are having sucrose, a disaccharide consisting of glucose and fructose. The glucose is dextrorotatory plus, rotates the plane polarized light in the clockwise direction. Fructose is levorotatory minus, rotates the plane polarized light in the anti-clockwise direction. Here you are having the glucose molecule linked to fructose through the linkage from carbon 1 of glucose to carbon 2 of fructose. What is important to be remembered or kept in the mind is the glucose is in alpha D plus glucose configuration, whereas the fructose is in beta form. That is very, very important. Fructose is in the beta configuration. So therefore, we have carbon number 1 of glucose linked to carbon number 2 of fructose through alpha 1,2 glycosidic bond. So if you will remember, this is the Havard structure of glucose 6-membered ring. This is the Havard structure of fructose, the 5-membered ring. The fructose is in the beta form, so you are previously having the OH above the plane. The glucose is in the alpha form, so OH was below the plane. So OH and OH on carbon 2 of fructose and carbon 1 of glucose have been involved in the glycosidic linkage. Therefore, there's a loss of water in the formation of this alpha 1,2 glycosidic bond. As we observe, in case of sucrose, the carbon 1 of glucose is not having a free aldehyde group. Like carbon 2 of fructose does not have free ketone group. Therefore, they are not able to react with Tollens reagent of filling solution. No reaction, no reducing property exhibited, and sucrose is therefore called as non-reducing sugar. That means sucrose cannot reduce Tollens reagent, neither filling solution, because it does not have free aldehyde or free ketonic group. They are involved in the glycosidic linkage. This bond cannot be broken. Therefore, the aldehyde of carbon 1 of glucose, neither ketone of carbon 2 of fructose can become free. They are not free, so they don't reduce Tollens reagent and filling solution. So that is why sucrose is called as a non-reducing sugar. Let's proceed towards the next disaccharide, maltose. Maltose is also called as malt sugar. Where does it occur? It's not a very common disaccharide in nature. It is present in germinating grains, and it is also present in small proportion in corn syrup. And also, if you will partially hydrolyze starch, we will get maltose. Maltose is a homodisaccharide. That is why it is composed of only alpha D glucose units. It is therefore made up of a simple similar glucose units linked together through 1,4 glycosidic linkage. This is the glycosidic linkage. Therefore, maltose is a homodisaccharide. There are the two glucose units, alpha D glucose linked together through a glycosidic linkage. So the structure of maltose is easily written if we remember the structure of glucose. I will again want the student to remember the structure of glucose. What was that? I had told you a shortcut way to remember the position of the OH groups. So how was it? Down, down, up and down. Here there was an OH. Look at carbon number 1 of this glucose part. It was having OH below, down, down, up, down. If you put the OH groups, you can easily put the bulky CH2OH in both the structures above the plane and finish writing the formula by putting hydrogen in other places. Carbon number 1 had OH below. Carbon number 4 also had OH below. They are involved in the glycosidic linkage and there is loss of water. That is why it is called 1,4 glycosidic linkage. That's what is found to be in maltose. Now, let us proceed towards lactose. Lactose is also called as milk sugar. The major source of lactose is milk. Hence it is called milk sugar. You also get it as a byproduct during the manufacture of cheese. Lactose is a heterodisaccharide. It is composed of galactose and glucose units. Mind you students, both are beta. Galactose is beta D galactose. Glucose is also beta D glucose unit. And in case of our lactose, there is a beta 1,4 glycosidic linkage. Let us check that out. That is what we are talking about. Carbon number 1 of galactose, this is the galactose part, this is the glucose part. Carbon 1 of galactose is linked to carbon 4 of glucose through beta glycosidic linkage. This is the beta linkage. So it is a linkage through oxygen. Now, glucose and galactose will differ only with respect to arrangement of the groups around carbon 4. In carbon 4 or at carbon 4 of glucose, H is above the plane, OH was before below the plane, but now it is involved in the glycosidic bond. Whereas in galactose, at carbon number 4, OH is above the plane and H is below the plane. So that is the difference between glucose and galactose. They differ in the configuration at carbon number 4. So carbon number 1 had H below, OH above in galactose. Carbon 4 had H above, OH below. So the OH and OH group are involved in the glycosidic linkage and hence we are getting the structure of lactose where there is beta 1,4 glycosidic linkage. This is what is observed in lactose. Now let us proceed towards polysaccharides. Polysaccharides are the compounds which contain large number of monosaccharide units which are all linked together by glycosidic linkages. And here polysaccharides are quite heterogeneous, and they are macromolecules with very distinct properties when you are talking about their with respect to monosaccharides, which are their building blocks. Generally, polysaccharides are amorphous or partially soluble or insoluble in water. The first polysaccharide which we are going to study is starch. Starch is the main storage polysaccharide of plants. Starch occurs mainly in the seeds of plants. It is an amorphous powder and insoluble in cold water. Starch is made up of two components. One amylose and the other amylopectin. Here, amylose is observed to be the water-soluble component of starch, and it is constituting about 15 to 20% of starch. Amylose has long unbranched chain with C1C4 glycosidic linkage, which is very similar to what you see in maltose. So let us check this formula. This is the structure of glucose actually, where you have carbon number 1, OH below the plane, carbon number 2, OH below the plane, OH above the plane at carbon 3, and at carbon 4, OH below the plane. The same observed in the other case. If you can remember, what was it? Down, down, up, down. Okay, so we are having C1C4, C1C4 glycosidic linkage formed where minimum 200 to 1000 such glucose molecules are arranged in long unbranched chains. This is the partial structure of amylose. So when we refer to the structure of amylopectin is the water-insoluble component of starch. It constitutes about 80 to 85% of starch. Amylopectin is found to be a branch chain polymer where it is built up of alpha D plus glucose units, which has got first alpha D plus glucose units all linked together in glycosidic linkage, which is found to be C1C4 glycosidic linkage. Later, branching starts occurring, and that gives rise to C1C6 glycosidic linkage. It is observed in the case of amylopectin, this branching C1, C6 branching occurs at every 24 to 30 glucose molecules. So we can understand this structure is very similar to amylose. suppose this is the 24th glucose molecule, there is 1,6 branching occurring, giving rise to the structure of amylopectin. So, the structure of amylopectin consists of C1C4 glycosidic linkage as well as C1C6 glycosidic linkage, and all are only alpha D plus glucose units. So students, they will generally ask you to write down the differences between amylose and amylopectin. So there are three important points: amylose, water soluble; amylopectin, water insoluble. Amylose is long unbranched chain polymer. Amylopectin is a branched chain polymer. Amylose has got C1C4 glycosidic linkage. Amylopectin would have C1C4 as well as C1C6 glycosidic linkage. Let us proceed towards the next polysaccharide, cellulose. It is a very dominating, predominant polysaccharide present in the cell wall of plants. Cellulose is also found to be present in wood, where wood contains about 40 to 45% of cellulose, as well as we have cotton containing about 90 to 95% of cellulose. Cellulose is a straight chain polysaccharide, and it is consisting of only beta D glucose units, which are all linked as beta 1,4 glycosidic linkage. So let us check the structure. This is the formula of glucose. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So carbon number 4 has got OH below the plane. Carbon number 1 of the next glucose molecule had OH above the plane, which are lost or reacting together to form water and giving us beta glycosidic linkage, where the linkage is between carbon 1 of glucose molecule and carbon 4 of the other glucose molecule. So it is indeed a linear polymer or a linear polysaccharide, which is going to be having extensive number of hydrogen bonds, which provides the rigidity to the structure of cellulose. The next polysaccharide which we are discussing is glycogen. Glycogen is the main storage polysaccharide found in animals. It is generally found in the liver, muscles of animals, as well as in the brain of animals. Therefore, it's also called as animal starch. The structure of glycogen is very similar to the structure of amylopectin. So this is how the structure of glycogen appears, as we have seen this on the screen. Now let us proceed towards the importance of carbohydrates. Why should we understand carbohydrates so much? One of the major significance of carbohydrates are they are the major source of energy for us, and they act as fuel molecules. Therefore, they are a major portion of our food is comprising of carbohydrates. The carbohydrates are also found to be storage polysaccharide in plants as well as in animals. In plants it is starch, in animals it is glycogen. So in us we store carbohydrates in the form of the polysaccharide glycogen. The next important significance is the cell wall of the bacteria and plants are all made up of cellulose. Carbohydrates also provide the raw materials which are required for many important industries like the textile industry, the paper industry, the lacquer industry. So it is a very, very significant carbohydrate or say biomolecule which we must understand better. Now, life is because of the presence of DNA. The nucleic acids comprises of the DNA and the RNA. The DNA is consisting of the carbohydrate deoxyribose and RNA consists of the carbohydrate ribose. So indeed, carbohydrates are forming the basic essence of life. The carbohydrates are also found in our biosystem along with the combination with proteins as glycoproteins, also in the combination with lipids called as glycolipids. They all are playing major role in communication and other body functions. Now let us understand the relative sweetness of sugar. Relative means we are comparing it, the sweetness of sugar with a standard. And the standard is taken as table sugar. Table sugar is nothing but sucrose. The value assigned is 100. Now we'll compare the sweetness of other carbohydrates with sucrose. Lactose is found to be having relative sweetness as 16. Maltose is still sweeter, 32. Galactose also is 32. Glucose is having 74. Sucrose, as we are taking the reference, is 100. And the sweetest carbohydrate is fructose, 173. So, the relative sweetness of sugars are all expressed with reference to sucrose or table sugar taken as the standard. So this is what we have in this chapter on carbohydrates, a unit of biomolecules. So the students need to go through the video once again, take down certain important points, write down and practice the Habot structure of glucose, fructose, lactose, maltose and sucrose. It is very, very important 2-mark question, as well as the structure elucidation of glucose, the open chain structure, how are you able to prove the presence of different functional groups, etc. in glucose. So they are all very popular 2-mark questions. So you need to practice them and revise them, read it and write and practice. So that's all we have in this particular chapter of carbohydrates. I am signing off now. Bye-bye.